Hello students and welcome to lecture 3 of unit 3. Here we will discuss about the dipole moment and molecular polarizabilities and how to measure those quantities. So let us first begin with dipole moment. So the first question is, where do we observe dipole moment? A dipole moment arises in any system in which there is a separation of charge. That is, wherever charges are separated, there is a probability of obtaining dipole moment in that system. For example, ionic bonds or covalent bond. Dipole moment, why do they occur? They occur because of difference in electronegativities between the two chemically bonded atoms. Thus, the dipole moment is nothing but a measure of polarity of a chemical bond between two atoms. So we have to understand the concept of electric dipole moment, which is a measure of the separation of negative and positive charges in any system. Now, since I say that it is a measure of separation of the charges, we have to understand that the dipole moment for a bond is a vector quantity and has both magnitude as well as direction. Since it is a vector quantity, its value can be 0 if they are in two opposite directions. That is, if the dipoles are in opposite directions, they will cancel each other out. Also, the direction of that dipole moment is parallel to the bond axis. So wherever there is the bond axis, it is parallel to that particular bond axis. For a single bond in a polyatomic molecule, suppose a molecule has many number of atoms. For a particular bond in that polyatomic molecule, that the dipole moment in that bond is known as the bond dipole moment, which may be different from the total dipole moment of the molecule. By convention, dipole moment is shown with a tail on the negative. Suppose there is a negative center and there is a positive center. So it is shown with a tail on the negative center and its head on the positive center. So the head is on the positive center and the tail is in the negative center. Okay? And the dipole moment is represented by an arrow symbol. So we have to denote it by an arrow symbol. And there is a cross on the positive center and the arrowhead on the negative center. So the arrowhead is on the negative center and the cross is on the positive center. So this shows the shift of electron density of the molecule. So it shows where the electron density is shifting. Mathematically, if you want to calculate the dipole moment, it is given by this particular formula. Dipole moment is equal to charge into distance separation. We will look into it further in the next slide. And the SI unit of measuring dipole moment is dBi, where 1 dBi is given in this particular value of coulomb meter. Here C is denoting coulomb and M is denoting meter. This is not centimeter, this is coulomb meter. Okay. For a chemical bond of two atoms having different electronegativities, since it is a measure of electronegativity difference also, so between two atoms of different electronegativities, the mu or dipole moment is given as delta into D, where delta is the magnitude of the partial charges. That is, if you have two atoms in a chemical bond, one having charge delta positive, the other has delta negative. So you have to take the magnitude of this delta, okay, into the separation of between delta plus and delta minus. That will give you the dipole moment for a bond. So when two atoms of different electronegativities interact, the electrons move from the initial position, because the more electronegative atom will try to pull the electron pair towards itself. So there will be a shift in the position of electrons towards the more electronegative atom. And the movement of electron is represented via the bond dipole moment. So how do you represent that shift of electrons from the initial position? We show it by the bond dipole moment. So let us try to understand once again. Suppose there are two charges. One is a positive charge Q plus separated by a distance r. is another charge Q minus. So one is positive charge, one is negative charge. So the dipole moment mu is given as Q, which is the magnitude of the charge, into R, which is the distance between them. So here also we have shown the same concept in a different manner. For example, if you see, suppose for ammonia NH3, we see that nitrogen is the more electronegative atom. The electron density shifts towards nitrogen, and ultimately the dipole moment is towards this direction, correct? And it has a specific value of mu, that is the dipole moment. Here I have also shown other examples of water. For water, how the net dipole moment varies, and for methane, CH4 molecule. Another important concept is that the presence of dipole moment also affects the physical property of any molecule. For example, if you take the case of 1,2-dichloroethene, when it is in the cis form, there is a net dipole moment. When it is in the trans form, the dipole moment cancels out and the net dipole moment is 0. Okay, so because of the presence of the net dipole moment, we see that it has a higher boiling point. The physical property, boiling point is a physical property, and it has a higher boiling point than the trans counterpart. So we also have to remember that the dipole-dipole interactions increases or decreases or affects the physical properties of a molecule. Now let us try to understand what is polarizability. Suppose there is a neutral molecule as shown in this figure. When you introduce an ion or a dipole, that neutral molecule can be polarized, and this process is known as polarization. And what is polarizability then? When there is a presence of electric field, the electron cloud can be distorted, as we can see here. Because of the presence of this ion or dipole having a specific electric field, the properly oriented positive and negative charges have been distorted and they have taken a particular direction. So the ease of this distortion, how easily this distortion can be done, is known as polarizability of that atom or a molecule. Why it is important? It is important because it helps to understand the interaction between non-polar atoms and molecules with other electrically charged species. As for example here, this was non-polar, but we see it's on interaction with a polar molecule, an ion or a dipole, how it interacts and what kind of a dipole is generated or dipole moments are generated. Okay, so how do we calculate this value? We calculate this value using this particular formula, where alpha is the polarizability of the atom and E is the strength of the external electric field. So let us read this. The created distortion of electron cloud causes the originally non-polar molecule, this one which was originally non-polar, to acquire a particular dipole moment. This is called as induced dipole moment. The dipole moment that has been induced is related to polarizability alpha of a molecule by this particular formula. So mu induced, that is the dipole moment induced, is equal to alpha polarizability into the strength of the external electric field. Now, how do polarizability correlate with interaction between electrons and the nucleus? So when the number of nucleus in a molecule is tightly held by the nuclear charge, so the nuclear charge actually controls how these charges or these electrons are distributed. For atoms with less number of electrons, we'll have very dense electron cloud. If the number of electrons are less, the electron cloud will be highly dense and it will have a strong interaction between electrons and the positively charged nucleus. So the positively charged nucleus will strongly hold on to the electrons, and there is also less shielding in atoms with fewer electrons, which contributes to a stronger interaction of outer electrons and the nucleus. When the electrons are held tightly in place in small atoms, when the atoms are itself small, these atoms are not easily polarized because those electrons are already very tightly held by the nucleus, so they cannot be easily polarized by external electric field. Okay, however, if you take a large atom which has many electrons in its in the outer orbital, okay, it should not be more than 8, correct. So for such systems, negative ions with excess electrons, they are very easily polarized, because the positively charged nucleus cannot actually control the charge distribution in the outermost shell or the outermost orbital. So such systems will have very diffused electron clouds, large atomic radii that limit the interaction of external electrons and the nucleus. So external electrons are available for the externally applied electric field for it to interact and thus polarize that particular molecule. So let us look at the factors that relate to polarizability. More the number of electrons, the less the control the nuclear charge has on its distribution, right? So there is increased polarizability of the atom. Again, if the distance of the electron from the nucleus is high, then also the nuclear charge cannot affect the outermost electron. In that case also, there is increased polarizability of the atom. And the molecular orientation with respect to the electric field, how the molecules are oriented in a particular electric field, that also affects the polarizability, except for those molecules that are tetrahedral, octahedral or icosahedral. Okay, so these factors are very important that we have to keep in mind while determining the polarizability in any given system. So with this, we conclude today's lecture. Thank you for your attention. If you have any doubts, I shall be available to clear all of them. Thank you once again.